Now, let's look more closely at unit conversions. First, of course, you have to know when a unit conversion is necessary. Here, it's good to go back to something we saw earlier. Most units can be broken down into a combination of distance, mass, and time. So what you need to do is look at the units in your problem and decide, do the distance units agree? Do the mass units agree? Do the time units agree? In other words, if you've got hours in one place, you don't have minutes somewhere else. If you've got kilometers in one place, you don't have light years in another. Also, remember to think about the units of the answer. Sometimes you'll need to answer a question with a particular set of units, so you want to make sure you're using the right units to get there. If your units don't agree, then you're going to have to do a unit conversion. Bruce is coming in here because failing to convert units is the single most common error people make in the math in this class. Always, always, always look for unit conversions. So once you've decided that you need to convert units, here's how you do it. Once again, this is a cookbook approach that will work. But if you already know how to do unit conversions, you should follow whatever procedure you're comfortable with. The way I look at a unit conversion is to treat it as a mini word problem, like a smaller problem embedded in the larger question you're answering. Then you go through a set of steps that are very similar to the ones we saw before.
We'll illustrate the steps with a simple, familiar example. How many days are there in 5 years? Your first step is to figure out which are your starting units and which you need to find in the end. In this case, years is our starting unit, and we need to end up with days. Our next step is the prediction. After we've changed units, should we have a bigger or smaller number than we had before? Remember that as the unit gets bigger, the number in front gets smaller and vice versa. In this case, we're changing from a big unit, years, to a smaller unit, days. So we expect there to be a lot of days, even in a small number of years. Now we can write an equation that connects the starting unit to the final unit. In our example, we can write 5 years equals blank number of days. As you write the equation, also leave a blank for the conversion factor. I think of a conversion factor as something that lives in parentheses and looks like a fraction. Its job is to cancel out the units that you don't want and put in the units that you do. So your ending unit will have to show up in the top or numerator of the fraction. Our next step is to fill in the conversion. We know that our conversion formula is 1 year equals 365 days. So those are the quantities that have to fill the top and bottom of our fraction. And we can see that the unit of year will have to go in the bottom, so it can cancel the unit from the term 5 years. That tells you that 365 days has to go on the top of the conversion factor. Frankly, the smart thing to do is to write down the units first and make sure you're getting everything to cancel out, then put in the numbers after. Does that sound crazy? That's really the order I do. At least when I want to get it right, that's what I do. Next, calculate the numbers, as the equation says, to get your answer. Be sure to write down your ending units. It's not an answer until you do. There will be times when you divide instead of multiply, but we'll look at that soon.
Finally, you do a sanity check by comparing your answer with your prediction. If you're expecting a much larger number, did you get it or not? Remember that the size of the quantity you're working with shouldn't change. So if it seems like you've got something that's a different distance, time, etc. than what you started with, then something went wrong. When we compare our answer to our prediction, we get that 5 years is a lot of days. So that makes sense.
Now let's try a unit conversion that is just a little harder. How many hours are there in 50,000 seconds? So in this case, our starting unit is seconds, and we're finishing up with hours. Next, the prediction. Even if you are quite uncertain what number of hours to expect, you can at least estimate that the number of hours must be smaller than the number of seconds, because each hour contains many seconds. Now write yourself the equation based on the starting and ending units. Did you get that? In this case, there are two parts to the conversion. A minute is 60 seconds, and an hour is 60 minutes. This means we will actually have two conversion factors, and you can multiply them in one after the other. The order will not matter as long as you get in everything required to cancel correctly to get the ending unit that you need. The only tricky thing is to be sure your conversion factors have the right thing on the top and on the bottom. You'll know if you're right by remembering the rules for canceling. You can cancel only when you have the same factor on the top as you do on the bottom. The rule for canceling units is the same as for canceling numbers. The most common mistake is to put in a conversion factor upside down. So if it's not working for you, try inverting your conversion factors. I've been doing this thing for decades, and I still catch myself making this mistake. Notice that to get this one right, we end up with our factors of 60 seconds and 60 minutes in the denominator, which means that on our calculator, we must press 50,000 divided by 60 divided by 60 again. We get 13.9 hours. Finally, do the comparison or sanity check. The answer says that 50,000 seconds is 13.9 hours, which makes sense, because although it's not a short time, the number of hours is less than the number of seconds.
Now it's your turn to do a word problem with a unit conversion. Once again, we've got a spacecraft traveling, but this time it's going to Jupiter. It's also moving a lot faster than the previous one. This one is going 16,000 kilometers per hour. However, to get to Jupiter, it takes 5 years. So the question is asking how far away Jupiter is. This is a word problem, so you should look over the steps we've gone through in the last few examples. You'll need to do a unit conversion. You should be able to tell what unit needs to change to what. Also, remember that you need to show your work on calculations or you won't get full credit. The last thing to cover here is that phrase, does it make sense? I ask this question a lot on assignments, and you should ask it too every time you do a calculation. So here's a set of things you can ask to help you decide if your answer makes sense. First off, do the units agree? If you've been keeping track of units, you should know whether or not you're getting a set of units at the end that fit with what you're calculating. If you're trying to find a distance, as in the last two examples, and you get kilometers per hour as the units of the answer, then you know you've got a problem, because kilometers per hour is a speed, not a distance. If I ask for a distance and you give me something else, it doesn't look good.
Next, is the answer the right order of magnitude? You don't have to have a lot of numbers memorized in this class, but you should be able to recognize when an answer doesn't make physical sense. If you find that a planet's mass is only 2 kilograms, then that should ring alarm bells for you. Bags of rice at the grocery store are bigger than that. Sometimes you may know that your answer has to be bigger than or smaller than some specific value. For instance, we know that Jupiter is farther away than the moon. In the first example, we calculated the distance to the moon. So in the second example, we'd better get a bigger distance. A lot bigger, in fact, or else something has gone wrong.
Finally, you may be able to look up the answer in your textbook or some other published source. Of course, you have to make sure you trust that source. So the takeaway message here is that you should be skeptical of numbers, including the ones you calculate yourself. Everyone makes mistakes in math, no matter how good they are at it. One of the key things that distinguishes those who are good at math is that they check over their work and recognize when they've made a mistake. If you do find that your answer doesn't make sense, there are 3 things you can do about it. First, go back and check your work and see if you can figure out where the mistake is. If that doesn't work, you can ask for help. I'm happy to help students who are trying to work on assignments and running into trouble. Usually, I find it's just some small mistake that's causing the problem.
Finally, if you don't have an opportunity to get help, you should at least write down that you recognize that there's something wrong with the answer, with some information on what you know should be there. That's actually worth a lot of credit. It tells me that you understand the science here, even if you're struggling a little with the math. And after all, this is an astronomy class, not a math class.
Unfortunately, I get many students who either leave the question blank or leave the wrong answer there and don't comment. If you leave it blank, I have no idea if you tried and gave up or just didn't try. In that case, there isn't much I can do to help you. You've got to show me what you've done. If you just leave the wrong answer there with no comment, then I assume you think it's right. So then, not only did you make a mistake on the math, you also didn't understand the astronomy. That means I have to take the points off for 2 errors rather than just 1. So that's our review of math skills in this course. Please refer back to these notes anytime you're running into math trouble in this class.
Here's another one of those making sense tables to fill out. This is one you'll be adding to all through the semester. By the time we get to the end of the term, you'll have every equation we're working with included in here. You'll want to keep this one handy whenever you're doing homework assignments or studying for exams. For now, fill in the first row, the part with the t equals d divided by v equation. This is really the same as d equals v times t, which we worked on earlier. You should make sure you say what each of t, d, and v mean, what units you would give those variables, and give a description of what sort of problem you would use this equation for.